Everyone, today we want to talk about two new rules for solving problems with circuits. We want to talk about Kirchhoff's loop rule and Kirchhoff's junction rule. With those two rules, I want to draw a circuit and discuss what the difference between each of those rules are. The first one, the loop rule, says that the sum of the potentials around the loop must be zero. And really it's just a conservation of energy. So if we graph that out, this is what we'll see. So if this is our simple circuit here, we've got a 9-volt battery with a 2 ohm and a 1 ohm resistor. It gives me a total resistance of 3 ohms. I've got 9 volts. That means that there must be 3 amps of current going through the circuit. Knowing that I've got 3 amps going through the circuit, the loop rule says that the sum of my voltage must add up to 0. So the first thing I want to do is go across the battery. If I go across the battery here, I'm going to gain 9 volts of potential, raise those charges to higher energy. As I take those 3 amps through R1, I can do I times R1 to see how much energy I lose across the first resistor, and then I can do I times R2 to see how much energy I lose across the second resistor, and in the end, as I keep going around that loop, I should end up with 0 voltage as I run back to the battery. So this should add up to 0. Double checking our math here, you know that the current is 3 amps and that the resistance is 2, so 3 times 2 gives you 6 volts you lose in that first light bulb, and we got 3 amps here in the second bulb and 1 ohm of resistance. So 3 times 1 gives us 3, and we've lost the other 3 volts in the second resistor. There's no voltage left, so you got to go back to the battery to gain more voltage. So if we graph this with voltage at different locations, when we're at the battery, we're increasing our volts all the way to 9. As we go through the wire might have a small loss in voltage because there's an electric field pushing those charges. But then when we get to R1, we lose 6 of our 9 volts that we were given. So we're going to have a big drop in potential. Then, right before we get to R2, there's another wire. So again, a very small loss in volts across that wire. When we get to R2, so we lose the rest of our 3 volts and we go back to the battery. So you can see we have voltage gains and voltage losses, but all our energy is conserved when we make it around that loop. So one thing we have to identify here is when we have gains and losses in voltage. So here's one way to look at this. If we have a battery and the current flows from the negative end of the battery to the positive end of the battery, we're going to say that we've gained a positive change in volts. However, if the current goes the other way, goes reverse from positive end of the battery to the negative end of the battery, we're going to lose energy into the battery, and this could be an example of a battery recharging. When you recharge your battery, you're sending current the wrong way across the battery, trying to put energy into the system rather than give energy to the charges to go out into the circuit. Setup number 2 deals with resistors. So when we come up to a resistor and we have current going in a certain direction, and if we say the loop moves in that direction, let's say that we've lost voltage in the resistor. We've lost energy, and the energy has gone into heat, sound, whatever we want. However, if we draw the loop in the opposite direction, we're going to have to say that there's a gain in voltage across that, just to keep our signs correct as we make our loops. Very similar to what we did with Atwood machines. When we did an Atwood machine, we picked a direction for an acceleration. If we got wrong accelerations, just means that our loop was backwards and current's flowing against the way that we actually thought. Keeping these two rules in mind, what happens at resistors and what happens at batteries, we want to go to Kirchhoff's second rule here. Kirchhoff's second rule is the junction rule, saying that all current that enters a junction must leave a junction, which again is kind of like the conservation of current. So you can see that we've got 2 junctions there. All that current hits the split, and some of it goes up and some of it goes down, or the reverse can happen. You can have 2 input currents and equal 1 output current here. I'll leave this question here for you. If I've got all these currents in these 5 different directions, the question is, what is the direction in the bottom wire? You've got 3 amps coming in, you've got 2 amps going out, 6 amps going out, and 4 amps going in. What must be the current in that bottom wire? So a way that I could write the junction rule here is I could simply just say that I1 must equal I2 plus I3. So instead of conserving energy now, what I'm doing is conserving the amount of charge. I can't create or destroy charge. I'm just going to split it up among the different branches that we have. If there was a 4th branch here with I4, I could just write I4 as my last current. follow Kirchhoff's rules around this setup. We've got two batteries here, battery 1 and battery 2. They each have internal resistances, and then you can see there's a resistance in the wires, something like this. So if we've got two batteries, let's say that EMF number 1 is the voltage of a brand new battery, and EMF number 2 is the voltage of a dead battery that you're trying to jumpstart with your car. So if I want to find the current that flows around this circuit, I'll say that this is a 12 volt battery here. Over here we've got an 11 volt battery. It has a lower terminal voltage, and it definitely is lower once we try to send current through it. The internal resistance will give as a value of 0.02 ohms, and the resistance of the actual jumper cables I'll give as 0.01 ohms. So if I want to pick a direction for this to go, I can pick the direction to be clockwise, counterclockwise, whichever way you want. I'm going to take my loop to be in this direction. So what I need to do is go around the loop now and make sure that I conserve voltage, conserve energy as I go around here. I don't have to worry about the junction rule for this one because there's no option for my current besides the path that I chose. First thing is I'm going to go across voltage number 1. If the current goes across the battery the way that I say it does, I can say that there's a positive 12 volts from battery number 1. Now if I want to find the voltage lost in the internal resistance, I'm going to have to do I times little r1. Then you can see I go all the way to the second battery. I'm going to have I times little r2 for my second voltage drop. But then I get to this second battery, and now I have current flowing the wrong direction across a battery. It means I'm recharging the dead battery. That potential is at 11 volts, so I'm going to have to subtract 11 volts. Then I'm going to go across that last resistor there, and that's going to be I times the big R. Loop rule says that all those volts must add up to 0 in the end, and so this is how we set this up. You can see I know voltages for the two batteries, and I know each of the resistances. So let's solve for I. Rearranging and doing some algebra, this is what you should get. I should get 12 minus 11 divided by each of the resistances in that setup. So if I do that, what you end up with is around 20 amps. So I have 20 amps of current that flow through that circuit. Seems like a lot of current, but what would be different if I switched the battery? If this battery was actually positive at this terminal and negative at the other terminal. Well, the only difference would be instead of a loss in volts, I'd have a gain in volts. And if you would do that, rearranging your algebra would mean that you add the two voltages together and divide by the resistance. And if you would add those two, you wouldn't get the 20 amps to recharge, you'd actually get 460 amps. 460 amps would be frying your battery, so you don't want to hook that up the wrong way. When you go to hook up your batteries to recharge a dead one, you put the positive to the positive, so you put red to red when you're jumping your car. Touch the black wire of the battery to the negative terminal, and you could touch the negative terminal, or you could touch actually anywhere that would ground the rest of the car. As long as red touches red and black touches black, you'll recharge your battery and you'll be just fine. Two batteries in this setup, and you can see there's multiple paths for our charge to go. We've got 3 different resistors and 2 different batteries. We're going to have to apply junction rule and loop rule for both. So like we said before, we need to pick which way we think current's going to flow. We need to pick a loop and then track the currents that we label. So I'm going to pick loop 1 here. Loop 1, I'm going to pick up and around on the inside. I'm going to watch the current come out of the 5 volt battery, across the 7 volt battery, across the 2 ohm resistor, and then back up that 3 ohm resistor back to the battery. That'll be loop 1. Loop 2, I'm going to take around this direction. So that'll be loop number 2. Again, coming out of the 5 volt battery, through the 1 ohm resistor, back through the 3 ohm resistor. And there's a third path I could choose. I'm going to choose that third path to be out around this way. That'll be my loop number 3. So I'm going to write loop rules for each of those, and I'm going to write one junction rule in the end here. I'm going to call these currents I1, I2, I3, since I see at least 3 different paths. Let's call I1 the current that goes out of the first battery. Let's call I2 the current that comes out of the second battery. And to pick a direction here, let's call I3 the current that goes around that last loop. So I've got 3 different currents here. They're all meeting at junction A, and looks like they're all morphing into current 1 that goes through the 7 volt battery. Why did I pick the direction for I1, I2, I3? I1 and I2, I kind of just went with the way the battery would push charge. For I3, I kind of thought of it this way. If I would follow current down to this junction, I know that some of the current would go up to the 5-volt battery and some would head into the 1 ohm resistor. So that's why I picked I3 to be the direction that I did. Let's set up loop rules for each of these. I want to follow each of these paths from battery through resistors and back. And when I look at that, I will need to highlight each thing in the path. So loop 1 says that all my volts must add up to 0 in the end. The first thing I go across is the 5-volt battery the right way, so I'm going to add 5 volts. Then I'm going to go across the 7-volt battery and add 7 volts. Then I'm going to go across the 2 ohm resistor with I1. So I'll have I1 times 2 ohms. And then I'm going to go across the 3 ohm resistor with I2. So now I've got loop 1 set up. I've got the 2 voltages and I've got the 2 voltages lost in the resistors. They're both subtraction because they went in the direction that I chose and they followed the loop that I chose. However, I don't know I1 or I2. That really doesn't help me. Let's write an equation for loop 2. Maybe loop 2 will help me. So loop 2, we said, was this setup. As I go around loop 2, I have the 5-volt battery involved. I've got the 1 ohm resistor and the 3 ohm resistor. So my equation's a little bit smaller. So 0 volts will equal 5 volts coming out of the battery. I'm going to have to then add I3 times the 1 ohm resistor. And the reason I'm adding is because the current is going against the direction of the loop that I picked. And then I go with I2 going back through the 3 ohm resistor, just like we had in loop 1. So again, in loop 2, I've got a voltage from the battery, but I've got I2 and I3 now, which means I really can't solve for either of them. So let's go and make a loop rule for the loop 3 is going to go around this outside. I'm going to go through a 7-volt battery, the 2 ohm resistor, and the 1 ohm resistor. And it looks like I'm going in the direction of all the currents I picked. Voltages have to add up to 0. And loop 3 is going to be my 7 volts from the battery, I1 times 2 ohms minus I3 times 1 ohm. So again, I wrote a third loop equation. I have a voltage from the battery, but I have I1 and I3. I don't have enough information to solve for any of my currents. So that's where the junction rule has to come in. The junction rule says that my currents must be conserved as I go through this loop. And if I look at the picture, I can see that I2 and I3 are meeting up to give me I1. The junction rule will actually be pretty easy. It'll say that I1 is made up of I2 plus I3. So looking at our 4 equations here, I have one equation with an I1 and I2, another equation with an I2 and an I3, one with an I1 and I3, and then we have our junction rule. What we'd need to do is solve for one of these currents. Let's solve loop 3 in terms of I3. So if I move 7 to the other side, I have negative 7 equals negative I1 times 2 and negative I3 times 1. So if I want to solve for I3, that should be pretty easy. Just some rearranging here. I can get rid of all my minus signs since there's negative all the way around. 7 minus 2I1 equals I3. So that gives me an equation for I3. Well, I can put I3 in here, and now I have I3 written in terms of I1. Let's see if we can find an equation that has I2 that will give us I1. So it looks like loop 1. Loop 1 has an I1, and it has an I2. We want to solve for I2. So I get negative 12 equals negative 2I1 minus I2 times 3. Let's solve for I2. I get rid of all my minus signs first, and I'll have 12 minus 2I1 all divided by 3 equals I2. Now that I have an equation written for I2, I'm going to put that into my junction rule right here. And what I get in the end is this. So I'm left with this. I've got I1 equals 12 minus 2I1 over 3 plus 7 minus 2I1. Now I have everything in terms of I1, and this will let me solve for current in my first branch. So doing some simplification, what you end up with is I want to combine all my I1s together, so I'm going to have to move my negative 2 and my negative 2/3. That gives me 3 2/3. I1 equals 11. If I want to solve for the current in the first one, you end up with about I1 being 3 amp. First setup, I1 is 3 amps that's going to walk out of that 7-volt battery. That 3 amps is going to walk across that 2 ohm resistor, but then that 3 amps is going to have to split up. So if we split that up, let's check I2 and I3. Well, I3, I'm going to put in my 3 amps that I got from my last equation, and I get that I have 7 minus 6. 7 minus 6 is going to give me 1 amp is I2. So this is 3 amps. I3 is going to be 1 amp. That means that I2 better be 2 amps. Let's go check this one and put 3 amps for I1 in there. So 3 times 2 is 6. We've got 12 minus 6 is 6 over 3 gives me 2 amps in the end for I2. So I've picked all my currents correctly as I went around that loop. 3 amps is what leaves the battery. 1 amp goes across the 1 ohm resistor, and 2 amps heads up to the 5-volt battery. So the whole point of using Kirchhoff's loop rule and junction rule is finding currents in more than one path, especially if you have more than one battery. So here's another setup with a 12-volt battery and a 5-volt battery. You can see there's 3 different resistors, and it looks like they've labeled I1 as the current that goes down that middle branch. I2 heads to that 5-volt battery, and just I itself is the one that comes out of the first battery. This is another good example problem. Try it for yourself, and we can go over your responses in class. One rule of thumb you can think of is that the bigger battery will drive the voltage for the entire circuit. So if you look, we've got a 12-volt battery and a 5-volt battery. I would say that the 12-volt battery is going to have a larger push than the 5-volt. So just remember Kirchhoff's 2 rules here, that you've got to make sure your sum of your voltages add up to 0 to conserve energy, and that you're going to conserve current through your junction rule, that all your current going into a junction must leave the junction, and they should help you in those problems. Good luck, and we'll talk next time.